Welcome to my fourth video on deriving the Poisson property mass function. So we have established the property mass function for Poisson distribution, which is this formula, using the linear differential equation, also the characteristic function in videos 2 and 3 respectively. So now we derive this property mass function using the moment generating function, which is defined as this. So again, to make this presentation self-contained, we restate the Poisson postulate and also the theorem 1. So if you already watched the video 2 or 3, you can skip this page and then just move to the next page for the proof directly. So the Poisson process means that we have an integer valued random variable nt, which is the number of arrivals in the time interval from 0 to t. And also we have a lambda value, which is non-negative. So our process satisfies the following 5 properties, which is also called the Poisson postulates. It's called the Poisson process with rate lambda. So the initial condition is that we have a time axis. So this is 0, and this is time t. And then we know that the number of arrivals at time equal to 0 is equal to 0. And also we have this independent increment, so which says that we have a number s here, and also we have say this length is t, so this point will be t plus s. All right, and then we know that the number of arrivals within this time interval is the ns. And then also the number of variables between s, also t plus s, is equal to this. And the independent increment says that these two random variables are just independent of each other. The third property is the stationary increment. So let's redraw this picture again. So we have this time t here. And also we have the, say, number s is here. And then this part is t plus s. Okay, and then the number of arrivals in this interval is the nt. And also the number of arrivals in this time period is the nt plus s minus s. And also you can see that this interval's width is equal to t. Also, this interval's width is also equal to t as well. So as long as these two interval widths are equal to each other, and then the number of arrivals in these two time intervals are just have the same distribution. So which is this. Okay, and next is like that, we want to focus on a very small time interval, which is the delta t. Okay, so this means that we still have this time axis. This is 0, and then this length is delta t. And then we focus on the number of arrivals in this interval. And you can see that the number of arrivals in this interval can be equal to 0, can be equal to 1, and also can be bigger than or equal to 2. So the chance that n of delta t is equal to 1, which is here, is about equal to lambda times delta t and then plus a little o delta t. So this is the so-called real events property. And also the chance that there are multiple arrivals in this time interval can be actually is negligible, which is equal to the little o delta t. So any process satisfy this five condition is so-called the Poisson process. And also we are interested in the number of arrivals within the time interval from 0 to t. So here's the statement for the 0, 0, 1. So the property mass function for the random variable nt actually follows Poisson distribution, and the property mass function is given by this formula. So we are trying to establish this result. So we will establish the previous result using the so-called moment generator function. So similar to the method in the characteristic function, we partition the interval from 0 to t into n sub-intervals, starting from j minus 1 times delta t and ending at j delta t. So basically what happened is that we have this 0 and then this t, and then we cut this one is the first part. So this is the first delta t, and then this is twice of the delta t, and etc. etc. And since the initial arrivals equal 0, and then the nt is also equal to the number of arrivals in this interval. So the nt is equal to the number of arrivals in this time interval, and then plus the number of arrivals in this interval, and then the number of arrivals in this interval, etc. etc. So we write this one as the sum of xj. And because the property B also the property C, which is the independent increment, also the stationary increment, so we know that these xj's are RID with the same distribution of x equal to n of delta t. So this part of discussion is the same as the case in the for the characteristic function. But there's a big difference between the moment generator function, also the characteristic function, as follows. So we can write the moment generator function of x as this. So if we write it out, it's equal to this one. And you can see that this part, so this which is the e to the y times x. So for any given value y, and since this x range is starting from 0 also to positive infinity, so e to the y times x can be very, very large. So in order to have a finite summation, and since this term is very large, and then we have to show that this term must be very, very small. So this is the major difference between the moment generator function, also the characteristic function. So we can decompose this summation as, so this is the case that when x equal to 0, and this is the case that when x equal to 1, and then this part is for x equal to 2 up to infinity, and also plus this little delta t. So now the goal here is that we want to show this term should be very, very small. To achieve this purpose, now for the event that x equal to lowercase x, which is bigger than or equal to 2, so we define, say, s1, s2, and up to whatever x sub x belongs to interval from 0 to delta t, be the x arrival times in the interval from 0 to delta t. And we claim that the chance that Si equal to x plus I plus 1 is equal to 0 for any value of I equal to 1 to up to x minus 1. So in other words, we say that all of those S1 through S sub x are different value. So this is the result we want to establish. Okay, so by the method of contradiction, assume that this claim is not true. And then the property that Si naught equal to Si naught plus 1 equal to S naught equal to a constant C, which is larger than 0. For some value of S naught, also for some integer value I naught. So which means that there are two arrivals at time S naught. So let n S naught minus denote the left limit of ns when this S goes up to S naught. Also define this n0 plus denote the right limit of ns, and when this S decrease to 0. And then we know that the chance that n0 plus bigger than or equal to 2, actually because of the stationary increment, so this is equal to the chance that ns naught minus the ns naught minus bigger than or equal to 2. And this event just contains the event that Si naught equal to Si naught plus 1 equal to S naught. But this property is equal to C by our assumption. So we conclude that the chance that n0 plus bigger than or equal to 2 actually is a constant value C, which is larger than 0. So this one actually contradicts with the property E that n delta t larger than or equal to 2 is equal to little o delta t. Because this property actually is larger than this property, but this property is kind of 0, but this property actually is larger than a constant C. So this is the contradiction. So this will conclude that all of these SIs are different. This is the crucial part. Okay, so we have a property that the nt equal to 1, the chance of nt equal to 1 is less than or equal to the chance that nt prime larger than or equal to 1 for any t prime is bigger than this t, also bigger than or equal to 0. So this is obvious. So for x value bigger than or equal to 2, and then we just try to estimate this property. So this property is equal to the event that n at S1 equal to 1, because there's one arrival at time S1. And then also there's another arrival at S2. So ns2 minus ns1 is equal to 1 as well. So it's equal to da da da. And also because we have the increment, we have the independent increment, and then this event is just equal to the product of the event that ns1 equal to 1, and then property that ns two minus n as 1 equal to 1, etc., etc. And each of these property is less than the property that the chance that n delta t larger than 1. So we have a 1 copy here, and another copy up here, and then there's an x copy up there. So we raise this power to the power of x. Okay, and then follow the property D, and we know that each of these property is just equal to delta lambda times delta t, and then plus little o delta t. Okay, now we just know revisit the moment generating function for x. So the moment generating for x is equal to 1 minus lambda times delta t, and then e to the y times lambda times delta t, and then also this summation. And we use this one and then minus this part, and then take the absolute value, which is here. So this will be less than or equal to the sum of each of this term, which is here, and then times, because this property is less than or equal to this property, which is the fact that we established in the last page, and then plus this little o delta t. So now, this one actually is the geometric series now. So you want to calculate the sum of the geometric series, and then the summation will be equal to the first term, and then divided by the 1 minus the ratio between two consecutive terms. So this is the first term. So this term is the term in this series when x equal to 2. And then we use the 1 minus the ratio between two consecutive ratio, which is this term. So remember that delta t is small. So this thing is just equal to the little of delta t. Because we have a square here, and then this is the delta t, so it's the delta t squared. So therefore, we established that the moment generating function for x is equal to 1 plus e to the y minus 1 times lambda times delta t, which is coming from this term, and then plus little delta t. And the moment generating function for nt is just equal to the product of the moment generating function for each of these xi. So we have this result here. And also remember that the xi are RID, and with the same distribution of x, so this product becomes to the moment generating function for x to the power n. So this one is just equal to this. So we have a power n here. So now we take the limit of delta t equal to 0. So we have this result. And also we make the transformation that n equal to t divided by delta t. So we have this form. And then also we follow the lemma 2 below. And then we know that this limit is just equal to this. So again, we calculate the moment generating function for Poisson distribution with the mean value equal to lambda t, so which is equal to this. And after this calculation, we know this is the case. So now we compare these two functions. And you can see these two functions are just identical. So which means that the nt, also the z, have the same moment generating function, implying that the nt, also this z, have the same distribution. So which says that nt is Poisson with mean value is equal to lambda t. The lemma 2 actually is the special case for lemma 1. In the lemma 1, we talk about this number a is a complex number, but now this a is only need to be a real number. So the proof actually is much simpler. So just pick a small epsilon larger than 0. So when this n is large, and we have this inequality holds. Because this little o 1 over n will be less than this epsilon divided by n, but also bigger than this negative epsilon divided by n. So now we take the limit for n go to infinity, and then e to the a minus epsilon. So we combine these two terms together. So we become to a minus epsilon. So e to the a minus epsilon is less than equal to the lower limit of this sequence, and also is less than or equal to the upper limit of this sequence. The upper limit of this sequence actually is equal to e to the a plus epsilon. And now we allow this epsilon go to 0. So this term converts to e to the a, and this term converts to e to the a. So this implies that this limit will converge to e to the a. So we finish the proof of lemma 2. So now we complete the proof of the property mass function or Poisson distribution using the moment generating function. In the next video, we will derive the property mass function using a binomial approximation, also through the moment generating function in the next case. Thank you for watching.